So, good morning, everybody. My talk will be on thermal characterization of AlGaN GaN HEMT using thermoreflectance method. Thank you to Eric to present some thermal aspects in the previous presentation. So the outline of my talk will be first an introduction. So why electrothermal measurement and simulation, and how to determine a thermal model. Then I will present the thermoreflectance setup, the presentation of the principle of the thermoreflectance, and the bench we have in XLIM. We will see first results on a microwave heater, result coming from thermoreflectance and validation of this first result with 3D FEM simulation as well as 3 omega measurement. Then we move on GaN HEMTs, 2 samples of 8x50 developments. And then we will see another measurement and comparison with gate thermometry measurement on a dedicated 2-finger HEMT GaN. And then we will conclude. So why electrothermal measurement and simulation? Today we have a very high power application with high power density with the increase of the frequency. And especially we can have more than 10 gigawatts per cubic centimeter. And sometimes we have poor material thermal conductivity, especially when the device is in package. And we need to cope with the temperature and to know exactly what is the temperature of the device for the application. So these self-heating are very important. Why? For the reliability of the electronic system first, the management of the cooling for the active module, and for the electrical behavior of the RF MMIC as it has been shown during this session. But the prediction of this temperature is very important, and then we can perform a coupled electrothermal simulation in circuit simulator. So how to determine a thermal model? 2 aspects. First, measurement technique. You have measurement technique like infrared, thermoreflectance, scanning thermal microscopy, Raman spectroscopy, laser interferometry, 3 omega, and some electrical method, which may depend on the device. If you have HEMT, if you have HBT, it will be totally different. So in red, you have the method that has been developed in XLIM. Spatial and time resolution are not always suited to the size and the use of the device, because you have very small device. Sometimes the hot area is inside the device, and it is very difficult to measure the real temperature, the temperature which impacts the application. Sorry. Next, the other way to have the information about the temperature is the 3D thermal simulation. But you need the knowledge of the thermal properties of material, which is sometimes very difficult because there are material are nonlinear. When you have very small dimension, it depends also of the geometry of the material. And you need to have the structure of the device, so you need to sign NDA with the company to have the structure and to simulate the device. And moreover, it gives the temperature on all the structure. So what temperature do you take after? A mean temperature, a peak temperature. This is important to go on and to have an equivalent temperature for the device. I have summarized in this table the main method of measurement. Here you can have scanning thermal microscopy, infrared, Raman spectroscopy, and thermoreflectance. You can see that the spatial resolution is very good for scanning thermal microscopy and also very good for thermal reflectance, because you can obtain a pitch less than 1 micrometer. And each of the technique have some good resolution, but if you want to perform time domain measurement, you can use either Raman spectroscopy or thermoreflectance. At XLIM, we have made the choice of thermoreflectance. So just to give you some principle of the thermoreflectance. In a material, you have a permittivity. With this permittivity, you can define a refractive index and the extinction index. And directly from these refractive index and extinction index, you can define the reflectance, which is the variation of the intensity between the input light and the output light. And this reflectance depends on the temperature of the surface that receive the light. So what is important to know is that the main relationship is that the variation of the reflectance is proportional to the variation of temperature, and this for a given wavelength. So we perform the measurement with a camera, so we can have a thermal coefficient that depends on X and Y, because we have not the same material on the surface. So, if we consider to continue with the thermoreflectance principle and with the test set, we have on the left side the reflectance variation, which is performed by measurement, and on the other side, the CTH, which depends on the material property, on the illumination wavelength, and the microscope numerical aperture. You have here on the left the spatial resolution versus wavelength, and you can see that you can reach a very good spatial resolution at low wavelength. But we need also to use a Peltier stage for fixing the temperature, and we need to use a 3D piezo stage to ensure the pixel alignment with temperature increase. Because when you perform the measurement, when you apply a variation of temperature, if the pixel move, you can ensure that the CTH you have measured is on the same pixel. So it's very important. So the measurement is performed in 2 steps. First of all, we need to determine the CTH coefficient. So we choose a wavelength. At the beginning, maybe we don't know the material we measure. So we perform several measurements for several wavelengths. And after, we decide what is the best wavelength that will give the maximum accuracy. So to begin, we fix delta T by applying 2 temperatures. So we fix delta T the reflectance variation is measured. So we can deduce CTH for all the map we are seeing through the camera. The second step, now we want to measure the temperature when the device is biased. So we apply power to the device. We measure the reflectance variation. And with the first step, we know CTH. So we can go back to the variation of the temperature. And this can be done for each point of the image seen through the microscope. The thermoreflectance allows also transient measurements. So we couple the electrical pulse with the LED pulse of the system. So we fix the electrical pulse. For example, here we have 100 microseconds and a recurrence of 1 millisecond to have time for the system to cool down. And the LED pulse is applied. In fact, it samples the excitation, the electrical excitation, and we have a delay. We apply a delay to move the measurement from the beginning to the end of the electrical pulse. So with this, we can acquire the temperature during all the excitation. This measurement is performed on several cycles in order to average the value of the temperature. And the precision for this measurement for gold metal, it's 0.5 degree. So this is a picture of the microsange thermoreflectance bench. So on this bench, we have a 4 megapixel camera. We have 4 light sources from 365 nanometers to 780 nanometers. We will see that the first wavelength will allow us to measure GaN device, especially, and the other one, the extremum, is for aluminum. And the best for gold is either 470 or 530. The resolution can be 300 nanometer, and the transient resolution up to 50 nanoseconds for a small pulse. We can also perform a wafer measurement with this kind of bench. So, first result, it concerns a microline heater with silicon and a line with gold. So we have first calibrate the bench because it's a gold metal. We have used a wavelength of 530, as shown here. For 530, you have a very important value for the thermoreflectance coefficient, so it's very interesting. And you can choose this one or this one. It's almost the same. So to go back, we have with this we perform a a time domain measurement until the steady state, and we get this kind of curve, and we can extract after the RTH, the thermal resistance for this kind of device. You can select some pixel inside the line and obtain the temperature, and you divide by the power you inject in the device, and you have the thermal resistance. We have validated this approach with a 3 omega method, which is very easy to use for resistor. And we have obtained a similar value for the thermal resistance. And moreover, we have performed a 3D thermal simulation of the line. So it's very easy device to simulate. And in each case, we have obtained a good result concerning thermal resistance and thermal time constant. Now we move on results concerning AlGaN GaN HEMTs. So to give you some information about AlGaN GaN HEMTs, so mainly when we bias the device, the heat source is located at the vertical of the gate, because you have a maximum of electrical field, and the current flow through the device, and this heat source mainly goes through the IC and under the device in the substrate. So these layers are very small, only few nanometers, and the GaN buffer is around 2 micrometers, and the buffer, the substrate for UMS device, it's about 70 micrometers. So we have a very strong difference between Z dimension and X and Y dimension. So this is a picture of the device. Here we have the picture for 3 different wavelengths, and as you can see here, you have an air bridge, so it's difficult to go through the air bridge, and we cannot measure above the air bridge, first due to the roughness of the gold, and because the hot area is under the air bridge. So we decide to measure at the end of the gate for this device, and to determine the temperature in this area at the end of the gate. So we perform 3 illumination, and we choose the best wavelengths to have the more important coefficient. This coefficient is for near UV illumination. The advantage of this wavelength is that the SEN passivation for this wavelength is totally transparent. So we can go until the AlGaN layer, so very close to the hot area. Here I present some results concerning the device. So the bias point is here on the IV curve. So we have the dissipated power, and we perform the acquisition of the temperature, the variation of temperature with this dissipated power on a window of 100 microseconds. So we can say that we need almost 100 microseconds to thermalize the device. I have a movie for, so I don't know if you can. Yeah. You have the evolution of the temperature with time, and you can see where that the temperature is higher here at the end. This is the topology of the device. So with this, the second measurement is performed. The first measurement was performed on 8 by 50 transistor from GH15. This one is on a 6 by 50 development. We perform on this the measurement here also at the end of the gate. So we measure 26 for the delta T, and we divide the variation of temperature by the power, and we can get also the thermal resistance for this device. So if we compare the thermal resistance of this device with the previous one, we can obtain the scaling factor between the development. So it's encouraging. So you have seen the difficulty with the average and the measurement, but we have also obtained for this the 8 by 50 the transient measurement of the temperature, and you can see that we can perform easily the measurement of the transient temperature with this method. Now I move to a 2 by 150 micrometer transistor. This is a special transistor. Why? First of all, it's very interesting because with large development, we have a window to access to the gate because the bridge is split, first of all. And on this design, we have access to the gate on both sides of the transistor. So it will be very interesting for us because with this access to the gate, we can use the gate as a resistive probe to measure the temperature electrically. And what we will do with this device is to try to compare thermoreflectance measurement with electrical gate-to-gate measurement, in fact. So, first of all, thermoreflectance measurement. So, we perform the calibration step. For the area of interest, which is here, near the gate. And we perform, so we know that here the best wavelength is IV, okay? So we measure, we perform the calibration, and then for different dissipated power, we measure the temperature and we extract with this temperature versus dissipated power. The second measurement is performed by using the gate, the resistance of the metal of the gate, and we applied a small variation in the two gates, only a few millivolts, in order to create a current and to measure the ratio between the voltage and the current and to measure the variation of the resistance. And we apply also VDS to have power inside the device. So first step, we apply various base plate temperature and we measure the variation of RG with T. And the second step, we apply several VDS and then we have RG versus dissipated power. So with these two curves, we can extract the variation of the thermal resistance with the dissipated power. And what we see is that it's not constant. So next slide, we compare now the results in terms of thermoreflectance with also RG, gate-to-gate measurement, and also nonlinear simulation. We have performed a nonlinear simulation of this device, and we compare the variation. And we compare also with other method, but the other method use the resistance of the channel and are not so accurate as the RG or thermoreflectance aspect for this device. Last thing that I want to show you is the transient measurement. So we perform measurement for several VDS and we measure the time domain variation of the gate current for 2.6 volt up to 9 volts. And with that, we say that temperature vary at the inverse of this what we see here, and we measure, we plot here the normalized temperature for 2 VDS. So what is interesting to see is that we have not the same transient variation. So why we have not the same transient variation? Because when we are at 2 volts, we are almost on a linear aspect of the device. So the power is, we have no hotspot. We have a large dissipation of the area for the device. And at 10 volts, the hotspot focus under the gate. And it's something that we can see if we take some hotspot, and if you enlarge the hotspot, you have the same kinds of results when you perform simulation. Just one slide before conclusion. Just to show you the accuracy of spatial and time domain. We have performed on, it's a 2-finger HEMT GaN from IEMN, given by IEMN. We have performed two measurements. One measurement on the gate metal with this wavelength, one measurement here with the near UV wavelength. And we have performed a time domain measurement. We have seen that the temperature is strongly different here. Here we are close from the hot area. We have more than 10 degrees. So we have a strong difference between the gate and this point, even if here you have maybe 1 micrometer. And then you can see also at the beginning the delay, because the heat needs sometimes to go to the gate. So with this measurement setup, you can see on one hand the delay and the variation of the temperature. So to conclude, I have presented some results concerning thermoreflectance and measurement on GaN HEMT that can be performed either in steady state or in time domain. We have obtained also good results with a dedicated device with two-gate access. Future works will concern the development of thermoreflectance measurement on a device with DC bias, but also with DC plus RF power. And we will also be interested to validate by our method by other methods like Raman and scanning thermal microscopy. And we will also examine the variation of the hot area with the bias power. We need to couple some physics-based simulation with thermal simulation to well understand what happened in the device. So thank you to the student who works with us and who performed the thermal measurement. Thank you to Christophe Chang and UMS January. Christophe for designing the two-gate access device, and UMS for providing HEMTs, as well as Farid Medjoub from IEMN. Thank you.
Long live India and France friendship.